There are multiple campaigns that are underway to improve the quality and intelligence of those systems.
The ability to reduce the amount of resources to create that special ability and run it, that really changes what's possible.
They can invest down this path to really put their product ahead, better competition for others, because they've developed this, this is far more efficient.
Hey, what's going on, everybody? Today is Tuesday, June 25th, 2024, and you're watching the Daily AI Show live. Today, we're talking about Kolmogorov-Arnold networks, or as Jyunmi says it, Kolmogorov-Arnold networks, because it seems like it needs to be more impactful. Or KANs for short. We'll probably refer to them as KANs during the show. They're a cutting-edge neural network architecture that offer improved efficiency, flexibility, and interpretability compared to traditional AI models. So before you go, why do you care, right? As a busy professional, why does this impact you? Well, so it's a possible revolutionary idea in terms of decision-making processes for providing more accurate forecasts. It has the ability to do more with fewer data parameters. And so it can be created faster. And the other thing that I think is really interesting, and we'll get to it later perhaps, is that it has what's called local plasticity. So often when you're training a model and you're moving forward, you have to choose, like, we're going in this direction based on historical data. This offers the ability, based on its architecture, to be able to shift and move in a different direction without losing the historical data. So with that, let me say that Brian's out. I'm Beth. We have Jyunmi and we have Andy so far, and we'll see who else comes. And as is always the case, Andy, can you give us a deeper dive and a foundation for our discussion today?
Absolutely. So this is important to all of us because as technology and AI advances towards artificial general intelligence, there are multiple campaigns that are underway to improve the quality and intelligence of those systems. And we know that, compute power alone is being added. And then, and thanks to Leopold Aschenbrenner, we can know that there are three primary drivers of those. It's compute, so physical compute. We're putting more energy and power against the training of these models. But there are also a whole class of what he characterizes as algorithmic improvements. And there are changes to the algorithms that are being used in the deep neural networks that are now, increasing their capacity to reason and to contain expansive knowledge and discriminate between knowledge about things that are silly and knowledge about things that are really useful to us. And the accuracy of all these systems and the suppression of hallucinations and all those things are progressing based on mathematics that some people in ivory tower institutions all around the world are thinking about deeply. And then the last one is the quality of the three main drivers is the quality of the data and the availability of the data that's used in the training of these models. So KAN, or Kolmogorov-Arnold networks, are a type of algorithmic improvement that actually is a change in the fundamental design of the neural network. So the neural architecture of a KAN is different from a multi-layer perceptron large language model. Now, multi-layer perceptron is a highfalutin term for the fact that deep neural network has many, many layers, multi-layers, and you feed the training data through those layers, and they adjust themselves in response to a loss function at the end that tells it whether it got the thing right or not. And then it has another function called back propagation that goes back through and adjusts the weights based on its score on that run through or forward pass through the model. So, excuse me. Now, KANs do something slightly different in the network architecture And I'll give you an analogy later of how that's done. But let's just say that the activation function term, we probably don't have enough time, but if we end up running through this, I'll talk about the activation function and its role in a deep neural network. But it's basically just to throw in some randomness in effect so that more and more neurons have to be involved in the capture of nuanced understanding, if you will. Okay, but we're going to set that aside. So the activation functions and backpropagation are things that we don't normally talk about on this show, but they are part of the terminology of how AI is trained to be able to do the magic that it does. Okay, so KANs are a new neural network architecture, and they are an alternative to multi-layer perceptrons, which is the focus of what most of the AIs that we are engaging with right now are. Big advance in efficiency and accuracy. So a KAN can achieve better accuracy than MLPs with many fewer parameters. Specifically, a KAN with 200 parameters can solve problems that require MLPs with 300,000 parameters. That's 100 times more parameter efficient. Energy efficiency is an outcome of that. So the compact size of a KAN in terms of its number of parameters required to represent knowledge and or reasoning capabilities translates to lower computational and memory requirements. And that's reduced energy consumption, which is a major issue for us all. Because as we've discussed in earlier shows, AI is going to consume a very substantial portion of the world's energy output. This has even led to people like Sam Altman saying, hey, we've got to solve fusion energy as we approach artificial general intelligence. Why? Because this is a very energy consumptive process to get to AGI. So this is relevant to edge computing. We've had discussions about edge computing where we want to move, instead of having big data centers in the cloud that are, have cooling requirements that are energy consumptive and also are, processing energy through their silicon chips, we want to reduce that energy consumption. And we want to be able to get it down to the point where power-constrained devices, like literally on your wrist or in your phone or on your desktop, can do these processes without all the power requirements that are there. And you can imagine in field operations where you want to have an AI that's driving a robotic vehicle or whatever, you have a limited amount of power on that vehicle. It's going to run out of battery at some point. So reducing power consumption on mobile devices, and I imply the wide range of mobile devices, not just the one that you carry around, the ones that carry themselves around, including robots. So robots might be really, really desirous of getting KANs rather than MLPs. Why? Because they're more efficient, they're more accurate, and they get all that done with a fraction, 1/100th of the power consumption. Okay, so what are these useful for? Edge devices, we've already covered that, but also scientific discovery. They are much better at fitting function curves in their sort of neural network understanding. They're much more accurate. And I'm going to throw out another term, which was totally foreign to me before a few weeks ago when KANs came around. But there's a great video on YouTube that a beautiful mathematician has created the visual graphics for, which is a very entertaining thing about splines. So splines are controllable functions that are applied in a KAN network in a way that makes it capable of learning very much quicker than the MLP, which has fixed functions as part of their training process. Well, the splines that are applied in KAN networks make it possible to be give you a higher representation of complex ideas with much fewer parameters, as we talked about.
Okay, so 2 questions. Jen is asking, remind me what MLP stands for?
Right. So MLP is multi-layer perceptron. So
Okay.
it'll make sense to you when I describe what a deep neural network is. It's layers and layers of these mathematical representations. And what you do is you feed data through them. The input to one layer is processed at that layer, and then the output of that layer is sent down to the next layer. And in that cascading process, like a pachinko machine, if you've ever seen those in Japan, they're flowing, data's flowing through all these different gates, and it's adjusting the weights of those. In the process of adjusting those weights, a perception or representation is created in that mathematical collection of weights. So by adding huge numbers of layers and adjusting weights with backpropagation, you get a representation, and that's a representation of a concept. But one of the problems with the MLP, the multi-layer perceptron way, is you can't look into it and say, okay, what's happening at this layer? And why did it come up with this idea? Or why is it giving this thing? So this is the subject of what's called interpretability. Interpretability is important because if you want to train a model for a very specific task, you want to know why it's making the decision so that you can provide it with feedback on the decision process and its representation, not just feedback on whether it was right or wrong at the end output. So you want to see what all the steps were in between them. Well, what KAN networks do is slightly different because it has a manipulable, a self-manipulable, not representation, I don't want to use that term, in the activation function at the edges between nodes in the network, it has the ability to create a representation is a larger concept than this. Now I'm confusing myself. Sorry, Jen.
We're good. We're good.
Okay. So I have an analogy, and this is not my analogy. This is a ChatGPT analogy comparing MLPs to KANs. So let's jump to that right now. But before I do, I'll just say that the last pieces of the sort of advantages of KANs are scalability. They exhibit faster neural scaling law compared to MLPs. So for the mathematicians who are working on these things, that lets them believe that this is like a more efficient architecture, just even for growing to larger size networks. And low latency is very important, again, on edge devices and on sensors and control systems, interpretation. All of that is, really important. It's going to happen faster. And you want really, really fast responses for example, autonomous vehicles. And when it sees something, it's got to process it very quickly. It can't have delays because it's got to put on the brakes very quickly. Okay, so here's...
Or incredibly impatient people who don't remember that more than a year ago, none of this was possible. And now we're just like, oh, it's taking so long to give me an answer that would have taken me a week and a half to find.
Right. Okay, so now we're at that point in the show where we're going to set aside all those complex terms, forget those, and now we're going to have a beautiful analogy crafted by an amazing deep neural network, which is an MLP, that understands what KANs are. Okay, so here we go. So imagine a city, and we have to lay out all the roads in the city and the intersections to improve the traffic flow through the city and make everything in the city accessible. Okay, in an MLP city, the intersections have fixed traffic lights. These are activation functions. The fixed traffic lights control the flow of traffic. The roads between the intersections are assigned weights that control how much data flows through each of the roads to go to the next intersection. Determines how much traffic or data can pass through. And the speed limits on those roads are fixed. So once you get on a road to go to the next intersection, you've got to go at the same speed. All right. By contrast, a KAN city, the intersections have no traffic lights at all. Instead, each road has an intelligent traffic controller, which is the learnable activation function using a spline function rather than a fixed function like a sigmoid or a ReLU, That's for anybody who happens to be listening to this, who actually knows what those things are. I want to just reference those. And those dynamically adjust the speed limit and the traffic on the roads based on the time of day, weather, and other conditions that it's learned. And those controllers are more flexible than simple speed limits and traffic lights. And they can control traffic in non-linear ways. Like they can, shuttle parts this way and parts that way in a way that responds to changing road conditions with more accuracy and fluidity. And it does that all much more efficiently than stopping all the data at every intersection and then deciding which ones can go through. Okay. Questions about that?
No, that makes perfect sense. And actually, modern traffic is flexible, right? Modern traffic, like traffic lights and that kind of stuff, ideally is flexible in a way. So, I notice it. I can, there's responsiveness to rush hour, right? I live outside Washington, D.C. So we get more time to put more cars through when there are like crazy numbers of cars.
So let me follow your analogy there about traffic, or ChatGPT's analogy about traffic, and say, suppose we didn't have human drivers and we didn't have traffic lights anymore, but we have autonomous vehicles that are driven by AI that know not just what's happening like 30 feet in front of it, but what's happening in the entire network of roads. Okay. And they can calculate, like Waze does today, what the optimum path through a, traffic system is. Well, that's similar to KANs, right? Where we're getting rid of the rules that we've imposed that are really limited, and instead giving learnable activations to the neural network that allow it to do some incredible things that go beyond the capabilities of the more fixed MLP. Okay, so great. Thank you so much on that. Let me also just say one thing about what, we've said why this is important, because it has so many advantages over MLPs. But the reality is this: just like electric today is obviously a better model of transportation power than combustion engines for lots of reasons, the fact that transformers have become part of a very complex ecosystem of services to deliver AI to the population is the same as the fact that there's all the distribution for fuel and all the, combustion engines out there. There's an installed base that's very hard to displace. So it may be that KANs, despite their great advantages architecturally, will never really be applied broadly because MLPs will improve and they have all this support behind them. For example, chips are being optimized, GPUs are being optimized by all the major players out there to run MLPs, which do, matrix multiplication as their primary compute. But spline calculations are different and would require a different kind of chip to be truly optimized. Will KANs ever be the big player in the scheme of AI? Maybe not. It may take 5 to 10 years for them even to find their way into the specific areas where they're much better. Edge devices, forecasting, like doing stock forecasting, for example, would be calculation, a predictive analysis that's better done on a KAN than an MLP. So it's important to understand that these are the kinds of advances. This neural, architecture advance is the kind of thing that will help us arrive at artificial general intelligence and beyond to super intelligence. But it's, there is an entrenched player here in the form of MLPs and all the companies and all the people who are doing it. And this reminds me also of how open source, like when you had Linux and it became open source, Linux was invested in heavily by many, many players. And so there wasn't a proprietary operating system out there beyond Linux that was used really by the technology community behind the scenes. And Linux got better and better and better and better. Why? Because there were so many brilliant minds being applied to that, rather than this one other possible operating system that may have occurred back then that was better than Linux, but never had the investment and the installed base to succeed.
Yeah, nice. And Jude actually offered a little bit of an analogy too. It's the difference between a classically trained musician versus one who plays by ear, right? So there's
pretty good. Yeah,
literally different scaffolding, right?
Yeah, good point.
So, Andy, I wanted to highlight the point where you say, it's sort of a versus. It's an uphill battle for Khan to get acceptance. It's not really a pushback, but I see the opportunity for the use of Khan to really fill in the gaps that we currently have with MLPs, right? So MLP-based AI, those are all the big players. That's OpenAI, ChatGPT, all of those. And we see those as large frontier models. They're integrated at that higher level, and then people build their applications. So in the sense for our audience, there's a lot of business applications that are built off of that, right? So from that viewpoint, for me, it seems to be more about where cons could flourish is in their application. So you mentioned the ability to see or interpret what's going on. That's far more clear on a con than an MLP. So if you have an application, let's say healthcare, where the decisions that are made at whatever level you implement an AI at, even if it's just like a back-end process for comparing, contrasting, analysis, that kind of thing, you really want to know how it's making those decisions, because potentially they have far-reaching or far more dramatic consequences. So you kind of want to understand that more than putting, if you're going to put a life in AI hands or along those that line, right? So I think that ability to see into it, and the fact that it can live on the edge, whether it's edge computing or if it's a matter of just doing more with less resources. So like you pointed out, less memory bandwidth, less parameters, all of those kinds of things. I see the on-device use for them is a perfect place. And I think if we look at what Apple was building for their ecosystem, this is an opportunity for a company like Apple or for a hardware manufacturer to invest directly in this, whether they make it proprietary or open source, but they can invest down this path to really put their product ahead, better competition for others, because they've developed this. Oh, this is far more efficient. I've got a con in my egg timer, as an example. But that I think that's where we're going to see a lot of movement potentially for this tech, because there's all of these edge computing or edge implementations in our life, right? Mm-hmm. Where the humans interact with it. Right now, we're really in let's try out this tool. There's a separation. It's part of our intelligence work, those kinds of things. But in our daily life, our home systems, our wearables, all of those kinds of things, our appliances, I think those devices where humans and the technology interact is the big advantage. Also, of course, energy use and things like that, like you said, Andy. But I think that's where we kind of want to focus if cons is going to become more used or more accepted or more developed.
Yeah.
Right. Right. So if we forecast ourselves, genuine forecasting, not Khan or the other flavors of forecasting, but if we forecast ourselves about the models getting bigger, right? You're going to use more parameters. In the traditional method, you're going to use more parameters. We talked about that with the Aschenbrenner situation awareness paper that we covered, what is time, maybe last week? What is time in the age of AI? But if we look at that and we combine that with something that is going to be able to get similar results with fewer parameters, right? So we're still increasing the capability, the capacity, the reasoning, the breadth of data. Now we're really starting to be able to, and with less computation resources, now we're really starting to be able to potentially circumvent what still seems like an incredibly fast trajectory, which is about every 6 months or every year, we're doing an order of magnitude more. But the constraint with that is the amount of data and the amount of energy and the amount of computation resources that are needed. So if Khan can be trained with less of those, with fewer of those, that is potentially a revolutionary concept in this arena. And again, like, wow, we're talking about like 6 months is too long for the half order of magnitude that we're going to engage in. But it is also true that 6 months is a very long time in these contexts. And certainly being able to reduce the costs would lower the playing fields.
I want to just say that Khan to me represents a smarter learning AI, right? It's better at learning than an MLP is. So it learns faster. It's got more horsepower in the brain, so to speak. And that's an advantage. But it's not the only kind of neural architecture, right? And MLP is not the only kind of neural architecture. And, for example, convolutional neural networks, which are used in image processing and image recognition, and can be reduced down to an ASIC, right? And do very fast response like the Khan can, low latency, very accurate image, target detection and that sort of thing. We've talked about that on a prior show. But a convolutional neural network is a certain kind of neural architecture that's really good at image processing.
Okay.
Optimized for that. Well, Khan is really versatile. It can do image processing and it can do all of the learnings that the MLPs can. And so I just want to also reflect on how far we've come and how far the academy has come, in effect, around AI. It's just astounding to me that, which combination of mathematicians and neural architects, came up with even this idea of applying that particular kind of math at the edges of nodes. This is way beyond me. I'm an English major, right? So I just can't grok those things. Speaking of grok, Grok, that company, not the network, the AI network from.
How are you spelling your phrase?
Okay, right? That
GROQ.
Oh yeah, I'm sorry. Right. Okay, GROQ. I'm sorry. Yeah, see, I get them confused myself. Why did Elon do that? I don't know, but maybe he had that name before Grok, the language processing unit developer, right? They developed a kind of neural network that's a multi-layer perceptron, but it's focused on language processing. And they developed a chip that's optimized for doing that, which they call an LPU instead of a GPU. GPU, graphics processing unit, happens to be good at matrix math, and that was used for images before, but now it's really, really good at doing language models. And that's what NVIDIA's Blackwell series is at the cutting edge of. Those are GPUs. Well, Grok had an LPU. But I get almost befuddled myself at what's going on behind the scenes when we can talk about, and with the assistance of AI, mind you, I mean, the research and the understandings that I have, limited as it might be, is a function of the availability of AI on my desktop right I could not have studied or been prepared to even discuss this with any kind of reasonableness without AI. That's advancing my capability. And now, now it's somehow got a representation in my neural network. So I learned those things. My brain has learned those things. But one of the things that's different about the brain's neural network is pruning. So our neural network, because it has a limited number of neurons and can't be expanded like these deep neural networks can in silicon, although we can attach an external memory to ours, hopefully one day with some connection directly to our brains. But because my brain has got the bowl is full. I can't keep all that stuff. So I'm forgetting a lot of stuff. Why? Because my brain is pruning away the things that aren't needed anymore, that I never refer to, that I never, connect to. And by the way, exposing yourself via AI to complex subjects is really important to maintaining the plasticity of your brain as you age. So, I'm grateful to AI for giving me the opportunity to both summarize and also to explore or dive deeper with my own interrogation of the AI to understand these things down to the level where I can grasp them. But going back to the people who are really at the cutting edge of these things and inventing them, my God, these people are way out there.
So we're grateful as well because we all benefit from Andy's deep dive into the subjects, and he brings those to us. Absolutely. Jyunmi, what were you going to say?
So what I wanted to kind of wrap around for everyone, a question for everyone is, what do you see? So when I look at AI, I tend to look at how is it going to affect my life? How is it going to affect the lives around me? And, ostensibly, business interests and things like that. But so I look at it as an applied sense, right? So I want to get everyone's opinion on what do you think their number one use case or application of a KAN is for whatever product, whatever application they see. What's your number one foresight into this?
So I'm going to say that, first of all, I'm going to break the question. I'm not just going to do one, but I'm going to say that as we're moving into an age of agents, right? We're moving into multiple AI representations, not meaning what Andy meant in the first part of the show. Multiple AI puppets. Let's call them puppets. They're agents. They do separate things, right? One is tasked with orchestrating a project. Another is tasked with identifying the resources and making sure all the resources are available. Another may be under that tasked with creating the resources or putting the resources in a format that is useful to the rest, right? So we're moving into much more like an orchestra function, and each of those could potentially be separate creations on it, using a separate architecture, using a separate set of data, using a separate process that would make it much more able to do its purpose, right? So the other thing we're talking about is artificial superintelligence. So one of those might be a super intelligent and a tiny narrow thing. So that becomes useful because that's not useful if it's super expensive to develop each of those, right? Or it takes like a giant computer to be able to house that function. So as we're moving toward that, the ability to reduce the amount of resources to create that special ability and run it, that really changes what's possible. That really changes. So we're no longer just using AI as like a resource for me to augment my abilities. We're now using AI as a coworker or a series of coworkers, so that I'm not just augmenting my personal abilities, I'm augmenting what I'm capable of doing what I'm capable of having done in the same way as if I expanded my business to hire a bunch of other people.
Mm-hmm.
That's my. Andy, what's your answer?
So the specific application vertical that I think is a good example of where a KAN might be deployed in favor over MLPs would be in high frequency trading. In the world of stock trading, there are these massive computers that are trying to analyze many stocks simultaneously in real time, what's happening with their movements, and to try to beat the moves and make tiny fractional trades that. And that's what they mean by high frequency, is like I buy and sell very quickly, like in seconds or microseconds. I do both transactions, but I'm always climbing the ladder. So the computers can do this very, very quickly. Well, a KAN can do that faster and more accurately for a large data set. And so I think that you'll see KANs show up in these sort of niche areas where low latency and very high precision are required. And that's one of the examples.
Nice.
I think for me, my primary example and hope is that KANs are developed for scientific applications, right? The fact that its main three qualities are accuracy, efficiency, and understanding, the understanding being the key one for me. I think scientists want to understand what the results are as much as what the result is, right? Yeah. So having that insight and being able to understand the more complex concepts and adjusting its tool set, so to speak, to solving of a problem will be highly desirable in scientific development. And so that's kind of where I want to see it, whether it be, disease treatment, drug or chemical creation, all of those kinds of things, material sciences, and specifically, those kinds of things is where I see it'll really shine.
Very cool. All right.
Awesome. So we are a weekly Monday through Friday show. Therefore, tomorrow we are doing another show. So on Wednesdays, we do an AI breaking news. We'll talk about what's happening in the news, important stories for you to know. And we always have some surprises that you're not hearing anywhere else. So we really hope that you'll come back and join us. You can find our newsletter at thedailyAIshow.com. And if you are not yet subscribed, we would love to have you join our community and tell your friends. Yay. And until then, thanks, everybody. Have a happy Tuesday.
Aloha.